Hey everyone, welcome back to another session with OneClass. My name is Bassam. I'm an engineering graduate, and today we're going to be going through some math problems, mainly algebra, at the high school and university level, the preliminary university level. Okay, so let's get started over here. Switch screens. Okay. So we're gonna verify the answers presented by the junior tutor, and then we'll go through a step-by-step process on how to get to that solution. So here we're asked, what is a linear pair? So a linear pair has to do with angles, and essentially, I believe there's a picture down here. So this picture right here describes what a linear pair is. But we'll go through what the junior tutor explained here, because the rest of these angle combinations are also important to understand. So here, a linear pair is a pair of adjacent supplementary angles. Adjacent means next to each other, and supplementary means that the measures of the two angles add up to 180 degrees. Okay, so just starting off, let's just number this as question number 1. So we're saying there's going to be two angles, let's say angle A plus angle B, and this will give us 180 degrees. Based on the definition. So here, adjacent and supplementary. As mentioned, adjacent angles are angles that are next to each other. If you are sitting next to someone in class or on the bus, you could say that you're adjacent to them. More specifically, adjacent angles share a vertex and have a common side. So here they're showing the definition of an adjacent angle. You can see that these two angles, angle A and angle B, are next to each other. And in this scenario, it's a 90-degree angle. Later on, we'll describe what a linear pair is. So, going on, supplementary angles are any pair of angles that add up to 180 degrees. Let's say you have to make a certain amount of money each month in order to pay the bills, but you only make a portion of that money at a regular job. You might find yourself looking for additional employment in order to supplement your earnings. So here they're giving you a metaphor of what the supplementary angles represent, and essentially it's two angles that add up to 180 degrees. And then finally, the combination of these two definitions will give us the linear pair. So here, another important fact is that the line here, let me read up above. Here is an example of adjacent supplementary angles that work together to create a linear pair. So here we can see that these two are adjacent to each other, right beside each other, and supplementary. They add up to 180. So the diagram that you really need to know is you just start off, draw a line, and then draw a dot somewhere, and then essentially you can draw this line anywhere. So let's say draw a yellow line. So let's say this is the line, and then we have angle A over here and angle B over here. We could also use the following. Let me look for the eraser here. So alternatively, what you could also say is an angle like this. So it could be also an angle over here, where you have angle A and angle B. So let's say this is A and this is B. But essentially, it's just two angles on this line separated as such right here, and you have them add up to 180 degrees. So I'll write DEG for degrees. Okay, so down here, the junior tutor presents an application. So for example, let's say we had A is equal to 75 degrees. So this diagram is incorrect. So let's say actually, let's rearrange these two. So we would say, let's rearrange. So let's say this is angle A over here, and then this is angle B over here. So angle A is 75 degrees. What is angle B? So you would use the linear pair equation above to figure out what angle B is. So you'd end up with 75 for A plus B. So we just subbed in 75 for A. This is equal to 180. And then b would equal 180 minus 75. So we just subtracted 75 on both sides of the equation. And then we end up with 105 for angle B. So this solution is correct. It correctly describes what a linear pair is and gives an example. So great job. Correct answer and explanation. And we'll mark this as correct. Okay, let's move on to question number 2. Okay, so this next question is asking us, use indirect reasoning to prove that log base 2 5 is an irrational number. So we're given log base 2 5. So here when it says base 2, usually when you write out log, you don't write out the base. But what is assumed in this scenario when there is no base written, the base is 10. So when you say log 5, you're essentially saying log base 10, 5. And these two are equivalent. But here they're giving us the base 2. So really, I'm going to erase this bottom part. So here we're trying to figure out, is it an irrational number? Is it an irrational number or is it not? So give me 1 second, let me grab something. Okay, so here we need to kind of define what an irrational number is, and essentially it's the opposite of a rational number is. So a rational number, I'll just write out the definition here. Is a number, so I'm just using this hashtag symbol to represent a number, that can be expressed as a ratio of 2 integers. So this is kind of the full definition of what a rational number is. And essentially we're trying to figure out, based on our reasoning, is it a rational number or is it an irrational number? And here they're indicating that it's irrational. We just have to explain why that's the case. So let me erase this bottom section. So looking at what the junior tutor outlined, so log ax equals y, so they're giving you kind of the template formula, is the same as a to the power of y equals x. So here log ax equals y. This can be converted into a to the power of y is equal to x. So using the same idea, we can convert this into this format. So we would say that this, so a is just 2. We'll say 2. Our y is unknown, so we'll just leave it as y for now. So 2 to the power of y is equal to x, and x in this scenario is 5 up here. So going on, we can see where a is the base and y is the exponent. Given the expression log 2 5, let's assume that it is a rational number, so they're making that kind of assumption. We can express the given as an exponential function, and then we can see that both 2 and 5 are prime numbers, and 2 is even and 5 is odd. So there's not really a number that you can plug in for y that would give you 5. You'd have to plug in an irrational number. You'd have to plug in an irrational number. So a rational number for y would be like 1, 2, 3, or any kind of so essentially any ratio of 2 integers. So it could be like a fraction or anything else. But in this scenario, you can see that because you can't plug that in for here, you know that log 25 is an irrational number. So just based on looking at this over here, we can say that log 25. I'm looking for the back button or the reverse button over here. I don't seem to find one. Oh, there it is. So log 25 is irrational. Okay. So we've verified that this is the correct solution based on our reasoning over here and kind of went through the step-by-step process. So we'll mark this as correct. Correct answer. Great job. And we'll mark this as correct. We'll move on to the next question. So this is question number 3. Question number 3. Okay. So here in this question, we're asked, how do you find the discriminant and how many solutions does it have? Just give me a second. Okay, so we need to kind of define what the discriminant is to kind of answer the how many solutions questions here. So here the junior tutor describes the discriminant as follows, and this is from the quadratic equation. So I'll write out the quadratic equation. It is negative b plus or minus b squared minus 4ac over 2a. So this is an important formula to memorize. It's just the quadratic formula. And it's used to find the solutions of an equation in the following format. So if you had an equation with this format, ax squared plus bx plus c is equal to 0, essentially you would have to plug in the constants in front of these variables, x squared and x and the last constant, into this equation to find the solutions. And the scenarios that pop up where you have real solutions or one real solution or no real solutions is described here below with the junior tutor. So they're saying the discriminant in this scenario is this right here. So this right here is the discriminant. And they represent it as capital D is equal to b squared minus 4ac. So we just got this from above. So this is just the definition of what the discriminant is. And essentially you have 3 scenarios as outlined by the junior tutor. You have when d equals 0, when d is greater than 0, and then when d is less than 0. So when d is equal to 0, so when this is equal to 0, we can see that this term over here would equal to 0, and we end up with just negative b over 2a. So if we were to plug in these values in this equation, we'd only really have one real root. So this is correct over here. So when d is equal, when the discriminant is equal to 0, we'd have one real root, and it would be this value. So, and then when d is greater than 0, so when this is positive, we can see that we have 2 real roots. And essentially it's saying the real term right here, essentially saying there's no negative underneath the square root, therefore the results of this formula will give us a real root. So if this was like anything greater than 0, so it could be 5, 10, anything, we could find a value over here that's real, and then we still have this plus and minus over here. So if we did the calculation for the first scenario where it's negative b plus whatever this value is divided by 2a, we get one root. So we'd have, I'll call it just the first root, and then we have the second root is when you use the negative sign. So the first root here, I'll write it out so it's more clear. So let me just draw an arrow. So if we draw the arrow over here, so the first root is negative b plus square root of b squared minus 4ac divided by 2, and then the next one is b, 2a, sorry, negative b minus b squared minus 4ac divided by 2a. So this is the first one, this is the second one. That's why we have two real roots when it's a positive value. And then finally, no real roots and the parabola does not pass through the x-axis. So what this is saying is, in this scenario over here, when this value is negative, we'll have square root of a negative number. And we can't do the square root of a negative number. So since we can't solve this, we'd say there's no real roots. The roots are essentially imaginary, but that's for a different topic. But essentially all you really need to know is when the discriminant is below 0, we know that there's no real roots and the parabola does not pass through the x-axis. So let's kind of outline what that means when we say the parabola doesn't pass through the x-axis. So just give me a second, let me clear some space. So if we had the first scenario, we'll say d equal to 0, so discriminant equal to 0. This would give us one real root. And then this situation essentially would be plotted as such. So we'd have an xy, and then let's use a different color over here. It would be something like this. And then the parabola would just be touching. So here, the solutions or the roots are wherever the function crosses the x-axis. So here it's only in one area. So that's why you have one real root. In this second situation, let's do this in green. So when d is greater than 0, we would have something like this. So it could be anywhere as long as it passes through the x-axis twice. We would have two real roots, and we know that the discriminant is greater than 0. And then finally, in the last situation, I'll do this one in red. We'd have something like this. I'm going to draw over everything, so we'd have something like that. So we can see right here, it doesn't pass through the x-axis at all. It's above it. It could also be below it, but like inverse, so it could be like this on the bottom. So this is when the discriminant is less than 0. So those are the three situations where you have one real root, two real roots, or no real roots. So we'll mark this question as correct. Correct answer. Great job. And move on to question number 4. So question number 4. Let me just give me a second over here. Okay, so question number 4. Okay, so this question is just asking, I guess, algebraic equations. Well, there's no real question, so we'll just go over this topic, algebraic equations, and kind of figure out kind of what this means. So let's go through what the Junior Tutor said over here, and then we'll follow on and look at other examples. So algebraic equations is a statement or mathematical statement of two equal expressions, the left-hand side and the right-hand side. The equation must have at least one variable to be called an algebraic expression, where the coefficient of that variable is a non-zero number. We say it is an expression if it does not have an equal sign. So here we have an example, 3x plus 12y plus 3. So here x and y are variables. The number 3 and 12 are the coefficients, and so on. So here another example, negative 2 over 3x equals y plus 4z. So z is just another variable, similar to x and y, plus 10. Okay, so operation algebraic equations is almost similar to arithmetic. We have addition, subtraction, multiplication, division, exponents, roots, and such. And solving equations, different properties of equality are done. So here they're giving some properties of equalities. that you can go through to kind of solve an algebraic expression. So I'll go through an example. Let's take this equation right here. Excuse me. So if we had 3x equals 12y plus 3. So let's say we're asked, isolate for x. What does x equal in this scenario? What you'd have to do is divide both sides by 3. So we'll use a different color over here. So we'll say divided by 3, and then divide by 3 on this side. So we know we end up with x on the left side, and then we have 12 divided by 3, which is just 4y, plus 3 divided by 3, which is just 1. So here we've isolated for x. We can do the same thing for y. So let's say we wanted to isolate for y. So we can start off with this right here. So we can subtract 1 from both sides of the equation. So we can say, let's say if we did -1 and then -1, we'd end up with the following. We'd have x minus 1 on the left side equals 4y. So plus 1 and minus 1 cancel each other out. And then finally we divide everything by 4. So this divided by 4 and this divided by 4. And then we end up with y, so we end up with x, 1 over 4x minus 1 over 4 equals y. So here we've isolated for y to kind of find that value. So this is kind of some examples of how you can manipulate algebraic equations, but essentially the definition is what we described up here, and it's essentially an equation with variables that have non-zero coefficients. So this is a correct explanation. So correct answer and explanation. Great job. And we'll mark this as correct, and we'll move on to the next question. Okay, so this is question number 5. Okay, so this question is asking how to find the x and y intercepts of x minus y equals to 4. So we have the following equation: x minus y equals to 4. So essentially here what you have to do is set certain values to 0, and from that you can use that to derive what the x and y intercepts. Let's look at what the Janine The Tutor said for this explanation. So let us first define what x and y intercepts are. X-intercept is the point where a line crosses the x-axis. So looking at this graph, it will be this point. And then y-intercept is where the line crosses the y-axis. So this is the y-axis over here. This is the x-axis that's horizontal. And then we have this function or this line passing through. So here we're saying we can see that the graph intersects x-axis at point 4, 0, and the y-axis at point 0 and -4. So they've kind of already said, they didn't really explain how you got these 4 and -4 values, but I think they go on further to explain this down here. So to find the x-intercept, we must let y equals to 0. So we know wherever that function crosses the x-axis, everywhere along the x-axis, y equals 0. So the y value is on this axis, which is 0 for the x-axis. So I'm just looking at it over here. So that's kind of why you substitute 0 for y to get the x-axis for this function. So you plug it in and you solve, you get x equals to 4 and so on. So let's go through this. So let's look at the original equation, which is this over here. So for x-intercept, I'll just call it x-int, set y equal to 0. So we'll have x minus 0 equals to 4. That'll give us x equals to 4. And then for y-intercept, we set x to 0. So looking at the original equation, we have 0 minus y equals 4. So 0 minus y equals to 4. And then since we have negative y, we have to divide by negative 1 on both sides, and we end up with y equals to negative 4. So we know that the x-intercept is x equals to 4, and the y-intercept is y equals to negative 4. And the point for that would be 4, 0. So at point 4, 0, that's the x-intercept, and at point 0, negative 4 is the y-intercept. So let's look down here for what the junior tutor answered. So the x-intercept is 4, 0, so similar to what we got. And then similarly here, they substitute for the y-intercept at x equals to 0. So just looking at this plot conceptually, the y-axis crosses the x-axis at 0. So they both cross each other at 0. That's why you substitute 0 for x. And then you end up with the following, and you get y equals to negative 4. And your y-intercept is 0, comma, negative 4. So correct answer great job. So one last thing to note for this question. You can see this right here is just the plot of the line. So you can see at 4, 0, this is where the function crosses the x-axis. So this is literally the function up here. And then at the y-intercept, we have the point 0, negative 4, which is over here. And that's kind of why you have this line. This line is this equation over here is represented by this line. So we'll mark this as correct. And we'll move on to the next question. Okay, so question number 6. Okay, what is the square root of negative 1? So square root of negative 1. So this is a very important thing to know. Essentially, this value is represented by I, which is just an imaginary number. So it's very useful when you're solving problems, depending on the problem. And it'll help you kind of solve for equations that give you a negative square root. So let's look at the junior tutor's answer. So an imaginary number denoted by the symbol I equal to negative square root of negative 1. And then here, or I squared is equal to negative 1. So how they get this is essentially if you square both sides of this equation, so you'd have square root of negative 1 squared equals to I squared. So we didn't change anything, we just square rooted both sides of the equation. This we squared, not square rooted. We squared both sides of the equation. So here the square root cancels out. We end up with negative 1 on the left side is equal to I squared. And this over here is also useful to know when simplifying. So let's actually go through these equations over here to help us kind of simplify. So the first example is I cubed. So I cubed, we can also represent this as I times I squared. So right away you can kind of see where we're going with this. Here we know I squared is negative 1, and we have I is square root negative 1. So we can just plug those in. So square root negative 1, and I squared is negative 1. And this gives us essentially negative square root negative 1, which is, so this could be, we could just keep this as I. So we'll just keep this as I, and we end up with negative I. Because whenever you're simplifying, you want a scenario where you don't have the negative square root in your final expression. So you leave the I over here, and then you end up with negative I. So looking at the junior tutor's answer, they come up with the correct solution as shown over here. So let's look at the next example. So for square root negative 25, we know that the square root of 25 is 5, so we can kind of split this out as such. So we have negative 1, square root of negative 1, and square root of 25. So we can see that this is equivalent to this. We just kind of separated out the negative, and we end up with the first is just this, is just I, as we described above. And we know square root of 25 is 5. So times 5, and this is just 5i. So looking at the junior tutor's answer, they provide the correct answer, 5i. And then finally, for the last example, so the last example over here is a little more complicated. So we're given negative 3 square root of negative 4 b squared z to the power of 6. Okay. So we'll do the same process. We want to split up the values underneath the square root and go from there. So this is equal to negative 3. We'll say times negative 1, square root of negative 1, times square root of 4, times square root of b squared, times square root of z to the power of 6. So right away we can see that this is I, square root of 4 is 4, and we can simplify the rest. So we have negative 3i, and then square root of 4 is 2, and then we have b. So if we have b squared square rooted, that's just b. If we had z to the power of 6 square rooted, this is equivalent. This over here is the same as saying z to the power of 6 divided by 2. So knowing this, we know we'll have z cubed. So 6 divided by 2 is just 3. So the 6 divided by 2 is 3 down here. So adding all the terms together, so we'll combine the negative 3 and 2, and we end up with negative 6 bz cubed I. So here the junior tutor obtains the correct answer as we've shown over here. So we'll mark this as correct, and we'll move on to the next question. So correct answer, great job. So from these examples, we can kind of see how this expression above is important to know to help us simplify equations with negative square roots. Alright, so question number 7. Okay, so alright, so let's get this question. What are the different inequality notations? So inequalities are used to relate two set of numbers, so this is what the junior tutor is describing. Inequalities are used to relate two set of numbers, variables, with each other. There are 4, and they give the 4 notations. So let's go through these notations. The first inequality notation is less than, which is as follows. So this could be used with just numbers. So we know 2 is less than 4. That's a kind of a simple example. We could also use it as follows. We also represent it as an equation, so we could say x minus 4 is less than 3, and then we can use this equation to solve for x, and that'll give us kind of for what values on the x-axis does this equation represent. So doing this quickly, you can see that x is less than 7. So if we had this on a graph, we know 7 is somewhere over here. And since the values of x are less than 7, we draw a line, a dotted line, because we know x does not equal 7, but it's everything less than 7, and it's this area over here. Okay, so that's kind of how you use the less than symbol. So let's go through the next inequality. Okay, so let's say we had greater than. So greater than is this way. So this could be, again, it could be like 100 is greater than 2. Or it could be 2 is greater than 1, stuff like that. We can also use an expression again. So we'll add variables to this equation. So let's erase this quickly. So we could say that x plus 3 is greater than 1. So we have x is greater than, so if we subtract 3 from both sides of the equation, we end up with 1 minus 3, which is negative 2. So if we draw a plot, we know x at negative 2 is somewhere over here. And we're saying all values greater than negative 2. So let me use a different color. So we're saying, we'll draw a line like this. And we're saying all values greater than negative 2. So something like that. And as you can see here, I drew a dotted line for negative 2 because we don't have an equal sign. So I'll use the same example for greater than or equal to. So if we had, let's say, oh, give me a second. If we had an equal to sign down here, if we just added this, here the main difference that you'd have to note is that, sorry, give me a second. So the main difference would be that this line would actually be solid. So there would not be a dotted line, it would just be a solid line. So I'm doing it would just be like that. So it's a little messy, but essentially just be a straight line. Here, I'll redraw it quickly. So we said we have negative 2, and we have a straight line, something like that, through negative 2, and it's this area over here that's represented by that equation. Okay, let's look at the final one. Let's erase all this. So the final example is the less than or equal to. So if we had as follows, so this could be satisfied by saying 2 is less than or equal to 2, or you can say 1 is less than or equal to 2, stuff like that. But really, you'd use this with variables. So I'll go over here for a second. Alright. So you'd have, let's say, an expression like x plus 1 is less than or equal to 4. And solving for this, you'd have x is less than or equal to 3, because you kind of subtract 1 from both sides of the equation. And drawing this out, you'd have as follows. So we know 3 would be somewhere over here. And then using a different color, so we know it could be equal to, we can draw a solid line right through 3. And then it's anything less than or equal to 3. So we'd say it's this region. And that's essentially kind of a quick run through all the inequality notations. So this is kind of a short answer of what they are, but there's a little more in-depth answer of how to use them and stuff like that. So great job. Correct answer. And we'll mark this as correct. Okay, so let's move on to question number 8. So question number 8. Okay, so here we're asked to kind of graph an inequality on the xy plane. So this is kind of a good example to run through. So we have the equality x is greater to, or x is greater than -2. So right away, just looking at the junior tutor's answer, we can see that -2 on this plot is over here. And then they draw a dotted line because we only have greater than -2. It's not equal to. If it was equal to, we draw a solid line. And then they highlight the red area over here is what is greater than -2. And then they go on to explain a vertical line parallel to the y-axis. And then they describe how they go about getting this. So a vertical line is dashed rather than solid to indicate that the line is not included, since the inequality defines every x value greater than -2. So if you're given this question on a test, you don't necessarily have to show all these grid lines. All you really need to do is as follows. So if you draw like a simple plane like so. Say here's the x, label your x and y. And then maybe you know that -2 is somewhere over here, so you just have to label that. And then I'm going to use a different color, so we know it's greater than and not equal to, just greater than -2. So we'll draw a dotted line going all the way through -2. And then to highlight the area that's greater than -2, you kind of just draw crosses all the way through. Oh, I've drawn a little over here. Erase that. Okay, and then something like that. So that's kind of one example of how to kind of do the inequality. So I'll do the next part in red, just to give you a better explanation. So if this was equal to, let's say this was greater than or equal to -2, then you'd have a solid line over here. So this line would be solid, and you do this region like that. But since it's not the case, we only really need the dotted line. Okay, so we'll mark this answer as correct. So correct answer. Great job. And we'll move on to question number 9. Okay, so question number 9. Okay, so we're asked how to find a scale factor. So let me just change the screen on this side. Okay, so question number 9. Excuse me. So let's go through what the junior tutor went through for scale factor and how to define and describe it. So let me do a quick skim over this. So they're giving kind of, have you ever wondered how machinists, etc. Before we begin this lesson, you will want to recall 2 math terms, similar figures and ratios. So here they give you kind of 2 figures, and they're trying to explain how the scale factor works through these figures. So here a ratio is a fraction that compares 2 quantities. This picture shows 2 similar 4-sided figures. Essentially they have kind of each side labeled over here, and they have like an enlarged figure of this, and it's scaled to this enlargement. You can see that this side is 3.2, this side is 1.6. So 1.6 times 2 will give us 3.2. Similarly, 4.6. So this is a little small. It might be a little tiny on your screen, but here it says 4.6. Here it says 2.3. So 2.3 times 2 is 4.6. And it's similar for the rest of the sides. So they just multiplied 2 by every side and drew this over here. So going on, in two similar geometric figures, the ratio of their corresponding sides is called the scale factor. So this is kind of the definition of the scale factor. To find the scale factor, locate two corresponding sides. So we can locate this side and this side. And in this example, the scale factor from the blue figure to the red is 1.6 to 3.2, which is a 1 to 2 ratio, which makes sense. This means that for 1 unit of length on the blue figure, there are 2 units of length on the red figure. And that's true. Okay, going on to this example down here. So similarly, they have the same idea, kind of. They have a bar graph. You have 2 on this side, and it's doubled to 4. You can see on this line. And then 1, 2, 3, 4 on this side, and 1, 2. So same idea, 1 to 2 ratio. Excuse me. Okay, let's scroll down over here. So they also give a cube kind of explanation, but really let's go down to so I'll give you kind of the simple explanation. This is kind of a long explanation, but essentially it's this definition that we highlighted over here. So this, in two similar geometric figures, the ratio of their corresponding side is called the scale factor. So if we had a square with a side of 2, 2, 2, 2, and we had another square that was a little bigger at 4, 4, 4, 4, we know that it's a 2 to 4 ratio, which is equal to a 1 to 2 ratio. Which makes sense, and that's kind of your scale factor, the ratio of their corresponding sides. So it could be any shape per se. So down here you can see that, I believe, yeah, so this example is a good example. So this is a trapezoid shape. You can see that it's flipped on this side, but we can see that if we look at this side, the angled side, we have 1.41. And then this side is 2.82. So 1.41 times 2 will give us 2.82. So we know this is a 1 to 2 ratio. Similarly for the base and the other sides. The only thing that in this situation this is flipped, but it doesn't matter for the scaled factor. And then in this situation we can see that this is not true. So 2.82, and then we have 4.47. So there's no, we can divide it by each other to see if this works, but here we have 4 and 4, so you can see right away that you have a 1-to-1 ratio on the long side, and then you have a different ratio on the angled side, and then you have a 2 to 4 ratio for this side. So you can see that this doesn't kind of satisfy the similarity of the shapes. You can say like a scaled factor for maybe one side, but really you'd say for the shape over here, the scaled factor is 1 to 2 in this situation. Similarly, in kind of a simpler shape for a square. So we'll mark this as correct. Correct answer and explanation. Great work. And let's move on to question number 10. Okay, so our final question for this session, question number 10. Okay, how to solve equations with infinite solutions or no solutions. So let's go through what the junior tutor explained here, and then we'll outline how to kind of conceptually think about this and how to use it to solve equations. So there's two situations, infinite solutions or no solutions. The third situation actually is one solution, but we're only focusing on these two. So solving an equation means getting a value for x. A solution is to an equation is a number that can be plugged in for the variable that makes the number statement true. Excuse me. Okay, so here they show the first example, infinite solutions. They have, I'm kind of just skimming through this to give you kind of the most important stuff of this answer. So y equals 2x plus 1 and negative 4x plus 2y equals 2. So we want to find the solution for these two equations over here. So we set them, we rearrange this equation, and then we set them equal to each other, and we get 2x plus 1 is equal to 2x plus 1. And we can see that the plot they drew out, it's two lines overlapping each other. So 2x plus 1 is this line, let's say, and then there's another line on top of it, but it's not really visible. And that's where you get infinite solutions. And then in the no solutions example, they outline this equation and this equation, and plugging them in, you end up with no solutions and you get two parallel lines. So let's just go through the first example. So if we're given y is equal to 2x plus 1, and we're given negative 4x plus 2y equals 2. So we'll rearrange for this equation first. So we'll say 2y equals 2 plus 4x, then y equals 2x plus 1. So we can see that this equation is identical to this equation. So if we set them equal to each other, we end up with 2x plus 1 equals to 2x plus 1. You could also say that 0 equals 0 if you kind of just subtracted 2x plus 1 from each situation. So this is another indication where you have an infinite number of solutions. So maybe it's a different algebraic equation and you're just solving through. But if you see also 0 equals 0, that is another indication that it's an infinite number of solutions. And essentially what this means is as follows. So let me get some space for this. So if we were to draw out the plot, what does this mean? So we have some line, let's say our first equation, which is this, y equals 2x plus 1. Let's draw this in green. It'll be something like this. This is a straight line. And then our next one, let's draw this in blue. So we drew 2x plus 1. It's essentially 2x plus 1 again. So it will be the same line on top of each other. So I haven't drawn these exactly on top of each other, but they should be exactly on top of each other. That's why you have an infinite number of solutions. And that's kind of an explanation of what that means. And then it's the situation where you have both sides of the equation equal to each other, or when you have 0 equals to 0, and you'll end up with an infinite number of solutions. Okay, so I'll go through also the situation that is not outlined in this question, which is one solution, and what does that look like before going to explain the next situation, which is no solution. So we know that one solution looks something like this. So we have line A, which is something like this, and then we have line B, which could be something like this. And our solution is over here. So the point where the two lines cross is our solution. So that's the second scenario. And then finally, the last scenario. So the last scenario. So I'll go through over here. So we have two equations. The first equation, y equals to 2x plus 1. And the second equation, negative 2x plus y equals 2. First thing you want to do is get it into the format of y equals mx plus b. So we'll move the negative 2x to the other side, and we'll have positive 2x plus 2. So here we just added 2x to both sides of the equation to end up with this. And then we set the two equations equal to one another. So we set 2x plus 1 equals 2x plus 2. 2x plus 1 equals to 2x plus 2. And right away we can see that this is not true. So whenever you have two sides of the equation, they're not equal. So if we took out the two x's, we'd have 1 equals to 2. And that just doesn't make any sense. So whenever you have in a situation where both sides of the equal sign are not equivalent to each other, so this is not equal. I'll just draw a line through this. We know that it's a situation where there's no solutions, and it's the two parallel line situation. So I'm just going to draw this out real quickly. So this situation is as follows. So we'll draw the plot, and our first line will be something like this, and our second line, I'll draw this in blue, will be something like this. And then these two are parallel. I've drawn these a little off, but they are 100% parallel. If they were not parallel, they would cross each other at some point, and you'd end up with the second scenario, which is one solution. But we know that in the no solutions case, they are parallel, and therefore we end up with no solutions. The two lines don't cross each other. And that's kind of an explanation of what this means. So here they give you a short answer. Infinite solutions to a problem means all the numbers are our solutions. Most of the time, the solution ends when both sides of the equation are equal to each other, which means equations belong to the same line. On the other hand, equations without solutions do not have answers. The variable usually cancels in the solution. Also, the equations are actually parallel lines. So this is the correct explanation. We verified it and went through the step-by-step explanation. Correct explanation and answer. Great job. Okay, we'll mark this as correct. So that was our final answer. Okay, so thanks for tuning in. Hope you found that those math problems were helpful. If you need any more homework help or tutoring needs, you can always go on OneClass.com. You can always subscribe to this YouTube channel to see more videos like this and answering different math problems and so on. And you can also visit the link in the description. I hope you enjoyed, and I'll see you in the next session. Goodbye for now.